Good morning, everyone. I am Kinam Kim from Samsung Electronics. My warmest greetings from Korea to everyone. I am privileged to attend 5th International Conference on Microelectronics Devices and Technologies. I would like to express my sincerest gratitude to the committee for inviting me as a keynote speaker. Although I'm not able to attend this exciting event in person, I am convinced this year's Microelectronics Devices and Technologies Conference will be a special venue for us in the semiconductor industry to make a bright future of semiconductor industry together. Now, let me start my presentation. Today, I'm going to present the following agenda: sustainable economic growth of future semiconductor industry by innovative technologies, meaning transforming physical challenges into opportunities. I will cover 3 topics. In part 1, I will discover opportunities of semiconductor industry led by digital transformation, simply saying DX. In part 2, I will examine the main challenges facing semiconductor technology today and efforts to overcome them through technological innovations. In part 3, I'll present the paradigm shifts in semiconductor manufacturing for successful sustainable growth of semiconductor industry. Throughout the history, civilization has been marked by numerous revolutions, each profoundly altering the way information is shared and accessed. Since the dawn of the writing, with the invention of the cuneiform writing system in ancient Sumerian around 3300 BC, the exchange of knowledge has evolved from spoken words to the use of written documents, bringing about fundamental changes in our ability to preserve and disseminate information. The 20th century ushered in groundbreaking achievement in electricity and electronic devices, initiating digitalization of information, which laid the foundation for another revolutionary era of the digital transformation in the 21st century. From PC to smartphones to the recent explosion of IoT, 5G, and AI, such as ChatGPT, we have witnessed unprecedented surge in the creation of digital data. That is, we are entering a new era, digital transformation, a transition that has been deeply penetrated into our everyday lives. At the basis of this grand opening of the new era, both hyperconnectivity and big data creation lie at the heart of it. Shown in the left chart, the number of connected devices is growing rapidly. By 2025, approximately 80 billion devices, which is 10 times more than the world population, will be connected each other. Furthermore, it will be staggering to see the total amount of data generated by this hyperconnectivity. For example, 97 terabytes of the data was generated in 2022, and it is predicted in this figure will double in only 3 years, soaring to 181 zettabyte. This wealth of information collected from edge devices such as smartphones is funneled into cloud systems for processing, regeneration, and storage. Therefore, in digital transformation era, high-performance computing capability and large-scale data storage are required for both edge devices and data centers, leading to continuous growth of semiconductor industry. As we went through the pandemic, we all realized that information technology based on semiconductor industry is indispensable for our daily lives. We are able to work, study, and play in online platforms, all powered by small semiconductor chips. The global market for semiconductors was valued at $590 billion in 2021. Semiconductor market is expected to grow continuously at an annual average rate of 7%, reaching to $1 trillion by 2030. Although global semiconductor industry is currently in downturn due to stagnant economy, the semiconductor market is ready for rebound, and it will be expected to continue growing in the mid to long term. This growth will be fueled by new applications such as IoT, AR, VR, smart car, and robotics. These applications will further evolve with the development of AI, such as large language model. Large language model based on AI is expected to create numerous new applications across the field, including IT, energy, transportation, commerce, finance, and beyond. In summary, as we go deeper into the era of digital transformation, I am quite sure we will witness the immense potential of the semiconductor industry. Over the past 50 years, global semiconductor market and its stringent requirements have been met through miniaturization technology, with which we were able to have realized ever-demanding higher performance, as well as ever-demanding lower cost per transistor. For example, compared to 1970s microprocessor, today's microprocessor speed increased by 100,000 times, and number of the transistors per wafer increased by almost 10 million times. Simultaneously, the cost per transistor per hertz was reduced by 46% every year. However, semiconductor industry is currently facing growing challenges. These challenges stem from the limitations of conventional miniaturization technologies, ultimately leading to higher investment. As a result, it gave us great concern on economics of semiconductor industry, especially manufacturing intensive sectors. Now, it is time to look at technological challenges as well as the relentless effort to address them in two key building blocks of semiconductor industry, which is data processing, that is represented by logic, and the other is data storage, which is represented by DRAM and NAND. Up to now, the evolution of logic, DRAM, and NAND has been achieved by self-fulfilling prophecy, that is Moore's law, which has been guiding us toward ever-demanding higher density, higher performance, and lower cost. However, as we march forward to physical limits of devices, the landscape poses ever-mounting technological challenges. In order to move forward beyond these barriers, technological innovations span from structure, materials, and fabrication processes are inevitably needed as we did in the past. In addition, recent challenges requires not only technological breakthrough, but also new way of approaches such as DTCO, design technological optimization, and even STCO, system technological optimization. Furthermore, at the same time, concerted effort across all stakeholders of semiconductor industry are imperative, because only through all encompassing innovation we can overcome these technological barriers and navigate into the uncharted new future. In following slides, I will talk about past, present, and future of the silicon technology innovation from the perspective of data processing and data storing. First, I will discuss innovations in logic technology for data processing. High performance, low power, small area, and low cost have been the driving forces behind the logic technology. However, around the turn of the millennium, CMOS scaling reached an inflection point where power performance gains from geometrical scaling start to diminish and physical limits emerged. The application of high-K and metal gate materials and embedded silicon germanium has made continued CMOS scaling possible. In addition to innovative materials, structural innovations like FinFET and MBC-FET have made CMOS scaling further down. In 2014, Samsung Foundry was the first company in introducing FinFET and in its 14nm node. With extreme ultraviolet lithography, simply saying EUV, CMOS can be pushed down below 10nm node. Now, CMOS is ready for 3nm technology node. Samsung are in mass production of 3nm using the world's first gate-all-around transistor of MBC-FET, meaning multi-bridge channel FET. As illustrated in TM image in the center, MBC-FET provides maximum electrostatic control of the channel so that MBC-FET improves transistor performance. At the same time, MBC-FET can enhance performance further by vertical stacking of additional channel layers. However, as we go beyond 2nm node, physical and technological challenges appear again. Generally speaking, the smaller a standard cell area, the better logic technology. Obviously, a smaller standard cell area can be achieved by scaling standard cell width and height, while the width is determined by CPP, so-called contacted poly pitch, which is the lateral distance between gates, as shown in upper left-hand figure cartoon. The height is mainly dependent on minimum metal pitch, which is also shown in upper right-hand side cartoon. In order to scale down CPP, we need to reduce the dimension of the either gate length or contact. However, decreasing the gate length induces large leakage current due to short channel effect. And decreasing contact dimension induces large contact resistance. On the other hand, in order to scale down standard cell height, we need to reduce barrel pitch, therefore metal width. This inevitably increases metal resistivity due to non-trivial surface and grain boundary scattering. Therefore, critical challenges in logic technology are short channel effects and contact resistance. In order to overcome these challenges, now let us look into innovative approaches by focusing on structures and materials. One approach is to decrease gate length without suffering short channel effect. The other approach is to decouple the gate from the MOL contacts. First, let me discuss gate length scaling approach. As mentioned previously, MicDAT provides the most excellent electrostatic control of the channel potential so that we can push down channel length further. The other is to adopt novel channel material, two-dimensional transition metal dichalcongenide, or simply say 2D TMD, which is only one monolayer thick, the ultimate thickness of the channel, which can provide ideal properties of channel, such as high mobility and small parasitic capacitance. On the other hand, vertical transport FET, simply saying VTFET, can stand out for its ability to place MOL contacts out of the plane. That minimizes contact resistance and short channel effect. However, high current driving capability and VT control need to be further explored. Further, scaling down standard cell height while maintaining its standard back-end of line, simply saying BOL scheme. It may be accomplished by utilizing backside interconnection technology. As the name backside interconnection implies, we utilize wafer backside as an interconnection platform for signals and power lines so that we can push standard cell effectively smaller standard cell height. And then MOS PMOS isolation, which is non-active device area, will be squeezed as much as possible as shown in forksheet structure cartoon. Ultimately, MOS PMOS isolation area can be completely eliminated by stacking MOS on top of the PMOS, like three-dimensional stacked FET, as shown in right-hand side cartoon. Summarize future logic technology, innovative device structures, new materials for device channel, and advanced metallization scheme like backside integration and MOS PMOS stacking will continue scaling standard cell area. Now, I will discuss innovations in memory technologies for data storing. DRAM is mainly used for high-speed temporary data storage. for data processing in computing systems. Therefore, higher density, low power consumption, and higher bandwidth are always main technological drivers of the DRAM technology. The achievements in DRAM over past 20 years have been remarkable. We have continuously shrunken the design rule by almost 60% from around 35 nanometer to 14 nanometer. It all comes from the innovations of structure of cell transistor and capacitor, including varied cell array transistor, simply saying MicDAT, vertically stacked capacitor, together with novel materials like high-K dielectrics, and advanced processes like EUV lithography, and so on. However, physical and technological challenges loom for scaling beyond 10 nanometer DRAM node. So, what are the challenges to sustain the DRAM scaling trend below 10 nanometer? There are 4 critical challenges. Leakage current, mainly due to gate-induced drain leakage, uncurrent of the cell transistor, cell storage capacitance, and data reliability. In following slides, let us look into innovative approaches in a little more detail by first focusing on structural innovations. As shown in the left figure, substrate of the leakage and uncurrent issues of conventional varied cell array transistor MicDAT structure became no longer tolerable due to its process variabilities. Innovative cell structures like vertical cell array transistor and vertically stacked cell array transistor, simply saying VSCAT, may provide solutions while maintaining process margins. In VCAT, we can separate two contacts, B-line and storage capacitor, and place each contact out of plane. Therefore, we can achieve the smallest DRAM unit cell area 4F square compared to 6F square in conventional VCAT. Here, F means minimum feature size. On the other hand, in VSCAT, as shown in right-hand side cartoon, we can place cell transistor and capacitance on the same plane to form single layer of DRAM cells, then stack them vertically to create multi-layer cell array, resembling the transition from 2D Fresnel NAND to 3D vertical NAND. I believe that these two structural innovations allow us to sustain DRAM scaling trajectory beyond 10 nanometer cost effectively. However, we should overcome challenges in suppressing leakage current due to its floating body effect and grain boundaries of cell transistor channel with innovative processes and materials. There are two approaches to deal with this leakage current. One approach is to suppress leakage current by developing advanced process and or novel materials. For example, we can greatly suppress leakage current by applying grain engineering, thus less grain boundaries in polysilicon channel. In order to have enough cell capacitance, high dielectric capacitor materials are inevitable. In this respect, ferroelectrics will be a good material choice for capacitor in future DRAM. However, we should overcome the challenges such as variability for ultimate scaling, such as below 5 nanometer. In order to moving forward below 5 nanometer, we need to go back to the basics and reconsider the constituent elements of the DRAM cell. Currently, DRAM cell consists of one transistor and one capacitor, so-called 1T1C DRAM cell. We may achieve the smallest and probably the simplest cell of the DRAM by taking capacitor away and storing data information either inside the channel region or inside the gate ferroelectric material. The beauty of 1T FET DRAM is that by vertically stacking 1T FET cell layers, we can realize high-density DRAM as much as we want in a cost-effective way. However, we should overcome challenges such as reliability, including cycling endurance and variability. In summarizing future DRAM, innovative cell structures, advanced processes, and materials for cell transistors and capacitors, and novel capacitorless 1T FET-based DRAM will scale DRAM technology below 5 nanometer and beyond. Now, let's switch gear to the flash NAND memory technology, which is permanent data storage. Ever demanding higher density and lower cost per bit are the main technological drivers of the flash technology. Therefore, throughout its evolution, innovations to NAND technology have focused on cost-effectively increasing bit density. Since we introduced vertical NAND in 2013, but first in the industry, the achievements in flash for the past 10 years have been remarkable. We have paved the way to continuously increase bit density about 30% in every generation by vertically stacking more layers, which mainly comes from the innovative VNAND structure and advanced high aspect ratio contact etching process and equipment. With the double stack and cell over peripheral structural innovation, we can achieve the smallest cell volume and mitigate the total stack height challenges. However, physical and technological challenges loom for stacking more than 1,000 layers VNAND. So, what are the critical challenges to sustain vertical NAND stacking more than 1,000 layers? There are 4 critical challenges. These are mainly coming from ever-increasing total stack height, including high aspect ratio etching, mechanical stability, low cell current, and interference between cells. As we stack more and more layers, ensuring the structural integrity is crucial to achieve our density goals. First, let's have a look from a structural point of view. As we stack more and more layers, high aspect ratio contact etching to form channel hole becomes extremely challenging because a vertical pitch of the single layer is no longer scalable. Therefore, we need innovative cell structure. There are 3 promising candidate structures: multi-stack, split cell, and trap-core cell structure. In multi-stack cell structure, we can mitigate the required process capability for high aspect ratio contact etching at the cost of additional repetitive processes. In split cell structure, bit density can be doubled while maintaining total stack height. However, there will be additional hard etching. On the other hand, in track per structure, vertical pitch of the single layer can be scalable because by cutting a charge trap layer, we can greatly suppress the interference between neighboring cells. However, these structural innovations can mitigate the challenges of stack height increasements, but it cannot stop total stack height increase because more layers must be stacked with ongoing evolution of generations, thus aggravating cell current and mechanical stability. We can mitigate these pressing challenges from the perspective of novel process and materials to tackle the issue of the low cell current. Probably we'll have two approaches. First, grain engineering. With recrystallization processes such as milk, meaning metal-induced lateral crystallization, we can increase the grain size of channel polysilicon, thus achieve significant mobility enhancement. Second, novel oxide semiconductor channel materials, which have a higher mobility than conventional polysilicon channel. However, this comes with the challenge of controlling the memory window and ensuring reliability. On the other hand, in order to improve the mechanical stability, we need low stress and low resistivity metal films without sacrificing excellent step coverage. Eventually, we may pursue to slow down the total stack height increasement. To this end, we need to decrease the operation voltages, such as program and erase, by adopting innovative non-charge-based storage devices, such as ferroelectrics or resistive memory device. In summarizing regarding future flash, innovative cell structures, advanced process, new materials for channel transistors, and innovative non-charge-based memory devices will enable flash to stack over 1,000 layers and beyond. In the landscape of semiconductor technology, the relentless march of progress brings forth unparalleled innovation. However, with its stride comes an undeniable challenge, that is, escalating cost of development. Of particular concern are the steep expenses associated with introducing cutting-edge fabrication methods and advanced technologies. These factors have contributed to a pronounced surge in investment cost, prompting need for holistic solutions that encompass both technological and manufacturing realms. Innovation isn't limited to technological breakthroughs alone. Pioneering ideas is also sprouting within the realm of the fab operations. I would like to shed light on a concept that holds immense promise of our industry, that is modularization. A revolutionary manufacturing approach, the modular fab, stands as a departure from traditional continuous production processes. Rooted in the concept of modular semiconductor devices, this method brings innovation to the forefront of the fab operations. One of the prime advantages is ability. to sustainably cut down production timelines. By creatively shortening manufacturing periods compared to conventional methods, the modular fab offers a dynamic response to ever-pressing demands of the time to market. Moreover, the modular fab has the potential to induce significant reductions in manufacturing costs, achieved through the streamlined exclusion of recycling and the verification of the modules that requires no further development. This approach ushers in an era of drastic cost efficiency. In the dynamic realm of the semiconductors, modularization and pursuit of the novel approaches are viable. Modularization within the context of each product involves dissecting intricate process into manageable modules and establishing dedicated fab operations for this modular unit holds the potential to not only slash manufacturing timelines, but also unlock substantial cost efficiencies. This slide presents a comparison between the existing production method and new modular semiconductor production with estimated turnaround time. By implementing a modular fab operation, remarkable improvements in TAT are evident across logic, DRAM, and NAND sectors. Specifically, the TAT reduction is approximately 40% for logic and DRAM and about 50% for NAND when compared to the traditional production method. These improvements yield significant benefits, including enhanced market responsiveness and a substantial reduction in manufacturing cost. Importantly, this approach mitigates the challenge of rapid investment cost escalation associated with conventional methods. This is paved the way for sustainable growth in semiconductor industry. Now, I'm reaching to my conclusion. For sustainable future of semiconductor industry, I discussed the pivotal role of semiconductors as a vanguard of digital transformation era and presented holistic solutions that encompass technological and manufacturing realms. This journey will continue, and I envision the thriving future of humankind, where the power of semiconductor innovation benefits the world, and where our innovation knows no bounds. Thank you. Thank you for your kind attention.